This video is going to be a continuation of your log page 1 on vectors. This is Learning Target 7.2. I can solve vector problems and resolve vectors into their rectangular components. We will be using vectors to solve navigation problems. We can use vector addition and trigonometry to solve vector problems involving triangles, which are often oblique triangles. A couple of definitions. In navigation, a heading is the direction that a vessel is steered in order to overcome other forces like wind or current. The relative velocity of a vessel is the resultant when the heading velocity and the other forces are combined. So here's example 7. An airplane is flying at an airspeed of 310 knots on a heading of 050 degrees. This is a true heading, so I'm going to go ahead and draw that. I'm making a drawing, a diagram. This is not going to be accurate. I'm not using a protractor and a ruler. So I'm going to draw an angle of about 50 degrees. And I'm going to call that's my vector. This is 50 degrees. And this vector is 310 knots. If a 78 knot wind is blowing from a true heading of 125 degrees, determine the speed and direction of the plane relative to the ground. So I'm looking for the relative vector. So I have a wind that is 78 knots and it's blowing from a true heading of 125. So here is 90, okay, 125, it's about here, close enough. Okay, that's probably a bit too long, so I'm going to make it a lot shorter so that it looks more accurate. Okay, so here is my 78 knot. Oops, wrong way. Okay, let me go ahead and say this since I made that mistake. The directions here say the wind is blowing from a true heading of 125. Okay, here's 125 degrees right here. That's a true heading. If the wind is blowing from 125, that means it's blowing in this direction right here. So the vector is going in this direction. If it was blowing to 125 degrees, it would be blowing this way. But this one is blowing from 125. Okay, so what we're going to do is we want to add these two vectors together. So I'm going to take this vector, which is 78, its magnitude is 78, and its angle there is 125, and I'm going to add it to this one, which is about here, in that direction. Okay? That gives me this resultant from here. See if I can get it to draw. To here. Okay, there's the resultant vector. Okay, so this is 78. I'm going to call this gamma. Okay, I don't know what that one is yet. Alright, so I've drawn a diagram to represent the heading and the wind velocities. Now what I'm going to do is use the law of cosines to find the magnitude of g. Okay, this is going to be my g here. I'm going to find the magnitude of g. Okay, so let's take a peek at this for a minute. If you will look at this vector and this vector, I hope you can see that they're parallel because they're going in the same direction. This is cutting across those two parallel lines, which means that this angle right here, if you can see that, I'm trying to draw lightly so that I can, so from here to here, is going to be the same size as gamma. Okay, this angle right here is the same size as gamma because alternate interior angles are congruent when you have two parallel lines cut by a transversal. So, I think I can find out what gamma is equal to. Gamma is equal to 125 degrees minus this 50 degrees right here would give me this angle right here, which would be 75 degrees. So gamma is 75 degrees. All right? So now I should be able to use my law of cosines to find the magnitude of g. Okay, so we're going to call this g over here. So the magnitude of g, and my hand's in your way right this minute, the magnitude of G is equal to 310 squared plus 78 squared minus 2 times 310 times 78 times the cosine of 75 degrees. Okay? And that's I'm going to take the square root of all that, because this is the magnitude of G squared. So the magnitude of G is going to be equal to the square root of all of that. This is your law of cosines, I'm sorry, times 78 times the cosine of 75. Okay, so this is just my law of cosines. Okay, that magnitude of G squared, okay, this is vector G, so the magnitude of G squared is going to be 310 squared plus 78 squared minus 2 times 310 times 78 times the cosine of 75. Take the square root of that to get the magnitude of G, which when I put that all in my calculator I get 299.4. Okay, that's 299.4 knots. Okay, so this is 299.4 knots. That's the magnitude of vector G. And this is, I'll make this a little bit bolder so you can see that that's a vector. Okay? Alright, so we have used the law of cosines to find the magnitude of G, which is the plane's speed relative to the ground. Okay, that's relative to the ground. Okay, relative to the ground. Alright, the next thing it says is find the heading of the resultant. So we need to find the heading of the resultant. So we need to know what is this distance right here. What is that degree right there? So let's call that theta. Okay, that's theta. Alright, well, this angle, I'm going to call it alpha, is inside of my triangle here. So I could use my law of sines to find alpha. Okay, and then if I took that and subtracted it from the 50, I would have my theta. Okay, so let's go ahead and do that. I'm going to slide this up just a little bit. I hope you can still see that. Okay, so I'm going to use the law of sines. So the sine of alpha over A is equal to the sine of gamma over C. All right, well, the sine of alpha over A is 78, equals the sine of gamma, which is 75, over C, which is 299.4. Okay, then I'm going to cross multiply. So I'm going to come this way with it so that you can see what I'm doing. So I'm going to say the sine of alpha is equal to 78 times the sine of 75 degrees over 299.4. Now, when I take that and put it into my calculator and take the sine inverse, I'll find out that alpha is approximately 14.6 degrees. Now remember, this is alpha right here. That's alpha. We need to know what theta is because we're looking for the heading. So now what we're going to do is take this 50-degree angle right here, 50 degrees, subtract our alpha from it. So 50 minus alpha, which is 14.6, will give me my theta, which is what I'm looking for. So 50 minus 14.6 is equal to theta. So theta then is 35.4 degrees. So now we have found the heading and the plane speed relative to the ground. All right. Resolving a vector. Two or more vectors whose sum is a vector r are called components of r. Components can have any direction. However, to resolve a vector, we always want to put the components perpendicular to each other. So we want two perpendicular components, one vertical, one horizontal. Okay, if you look at the picture here, you can see vector R is here, and the two components are vector X, which is horizontal, and vector Y, which is vertical. Okay, the force R that's exerted to pull this wagon can be thought of as the sum of a horizontal component, which is a force component, okay, that's vector X, that moves the wagon forward, and a vertical component, force Y, that pulls the wagon upward. So you're pulling it forward and upward, and that gives us vector R, the components of vector R. Okay, example 8. Heather is pushing a handle on a lawnmower with a force of 450 newtons at an angle of 56 degrees with the ground. Letter A says to draw a diagram that shows the resolution of the force that Heather exerts into rectangular components. So the first thing that I notice here is that I have a downward force on the lawnmower of 450 newtons. Okay, downward force. And the angle is at 56 degrees with the ground. Okay, so we're going to resolve this into two rectangular components. So I'm going to erase a little bit because I made that too long again. So if I'm pushing downward, okay, then I'm moving the lawnmower horizontally forward, and then I am pushing down on the handle. Okay. This is 56 degrees, this is 410. So now, if I want to find the rectangular components, I need to find X and I need to find Y. Okay, so we're going to find the magnitudes of the horizontal and the vertical components of this force. So to do that, I can use my right triangle trig. Okay, I can say X is equal to the adjacent over the hypotenuse, which is the cosine of 56, is equal to X over 450. Okay, 450, oh, that's not degrees, I apologize. That's newtons. 450 times the cosine of 56 degrees is going to give me my X. Okay, and when I put that into the calculator, and I get X is equal to 252 newtons. Now, I do want this to be, this is the magnitude of X, so I want you to understand that this is the magnitude. It's not the length of X, it's the magnitude of X. So 252 newtons. Okay, then when I do Y, I'm going to slide this way just a little bit. Y is the opposite over the hypotenuse, so that's the sine of 56 is equal to Y over 450. That's newtons. So 450 times the sine of 56 is equal to the magnitude of vector Y. So technically we should put magnitude here and here. So the magnitude of Y is going to be 373 newtons. Okay, so now we have found the magnitude of the horizontal and the vertical components of the force.